Okay, so now after learning operator overloading, we will move forward to templates. Now our focus will be on templates in C++, which allow us to write generic and reusable code that can operate with any data type. Specifically, we will explore function templates. We will cover the syntax and definition of function templates, looking at how they allow functions to work with multiple types. Additionally, we will discuss potential compiler issues you might encounter when using templates. Then we will learn uh, class templates, which enables us to define classes that can handle any type. We will use an example of an array template class to illustrate this concept. Then lastly, we will explore how templates interact with inheritance, with a focus on a partially filled array template class example. So now by the end of this session, you will have a clear understanding of how templates work and how to effectively use them to create flexible and efficient C++ program. Okay, so C++ templates are a powerful feature that allow you to define very general, flexible functions and classes. Instead of specifying actual types, templates use type names as parameters, which are then determined precisely at compile time rather than runtime. This flexibility enables you to write code that can work with any data type. It makes both reusable and adaptable across different scenarios. Here, let's consider a swap function, which swaps the values of two integers. If you see here in this code, void swap integer and variable 1, integer and variable 2. This function works perfectly for integer types, but the logic would work just as well for any data type, whether it's float, double, or even user-defined types. However, as it's currently defined, it only applies to integers. To make this function more flexible, we can turn it into a function template. By doing so, we will swap to work with any data type, making our code more reusable and adaptable. Now in this slide, we'll see an example of how you could overload the swap function for character types. While this works, notice that the code is nearly identical to the integer version, only the data type has changed. Overloading requires writing separate functions for each type, which can lead to code duplication. This is where function templates shine. Instead of writing multiple overloaded versions, we can write a single template that works with any data type, reducing redundancy and making our code more maintainable. Here's how we can generalize the swap function to work with any data type using a function template. If you see, we write template, then class T, and then the function swap. So here we have a template prefix. The first line, template class T, tells the compiler that this is a template. The T class is a type parameter, meaning it can be replaced with any data type when the function is called. Then we have flexible typing. The swap function can now swap values of any type, integer, character, double, etc., anything, without the need to write separate function for each type. So in this context, class is synonymous with type name, and it doesn't refer to the abstract data type class, but rather to a placeholder for any data type. So this is an example for the template function. So this example demonstrates how the swap values function template can be used to swap values of different data types. If you see here on line 5 to line 12, we have the template class T, then swap values function, then the rest of the function. So, and then we have a integer main function. First two integers, integer 1 and integer 2, are defined and swapped using swap values, integer 1, integer 2. Next, two characters, symbol 1 and symbol 2, are defined and swapped using the same swap value function. This example shows how a single template function can be used to handle different data types like integers and characters and any other without needing separate functions for each type. The output confirms that the values have been successfully swapped for both data type. If you see the output here, so first if you see original integer values are 1 2, then swapped to 1, then for character it is AB and then swapped BA. So when defining a function or class template, the line template class T is known as the template prefix. Meaning of class. In this context, the word class doesn't refer to a C++ class, but rather means type or classification. It indicates that T is a placeholder for a data type that will be specified later. So you have to keep that in mind. This class is not the C++ class. It is the classification or type. Then type name versus, if we say type name versus class, C++ allows you to use the keyword type name instead of class in the template prefix like this, like template class T. Instead of class, you can write type name. So many programmers prefer to use class out of convention, even though both terms are functionally equivalent in this context. Understanding this distinction helps avoid confusion between these uses of class and its more common role in defining classes in C++. Okay, so here is another example. T as a placeholder. If we say in the template prefix template class T acts as a placeholder for any type. This type can be predefined like integer, double, etc., or user defined like a custom class in C++. So then inside the function body, T is treated just like any other type. It can be used to declare variables, define parameters, and so on. Then while you can use any identifier instead of T, it is common practice to use T as the placeholder for the type in templates. This convention helps in making the code easily understandable and consistent. Okay, so here if we see the function template definition, the swap values function template is essentially a blueprint that can generate a large collection of specific function definitions, one for each possible data type. So the compiler doesn't generate all these definitions upfront. Instead, it creates a specific definition only when the template is used with a particular data type. But it's as if you had written out a version for every possible type. This approach allows you to write a single template function definition that works for any data type you might need, avoiding the need to write separate functions for each type. Here, when you call swap values integer 1, integer 2, the C++ compiler automatically generates a function definition that works specifically with the integer type based on the template. This process occurs similarly for any other data type you use with the template, whether it's float, character, or a user-defined type. No special syntax required here. You just You don't need to do anything special when calling a function template. The compiler handles the generation of the required function definition based on the types of the arguments passed. Again, stuff 1, we have the functions show stuff, and then we have stuff 1, stuff 2, stuff 3. These templates allow the function to work with different types of for stuff 2 and stuff 3 while maintaining flexibility. Here if you see the show stuff call, when you call show stuff to 3.3 4.4, the compiler generates a specific function definition where t is replaced with double because the second argument 3.3 is a double. If you see here, this is the output. If you see displays, it displays 2 3.3 4.4. This demonstrates how the function adapts to different types dynamically based on the template parameters. So it is possible to define a template with multiple type parameters, as shown in the syntax template class T1, class T2. This allows you to create functions or classes that can handle different types for different parameters. In many cases, you will only need one replaceable type, making multiple type parameter less common. However, they're useful when different types need to be managed within the same function or class. All type parameters declared in a template must be used in the definition. You cannot declare a template parameter and then leave it unused. This would result in a compilation error. So to define templates, there are some strategies. So if we go step by step, first it develop normally, like start by developing the function using actual data types like integer, float, etc. This makes it easier to write and test the function since you are working with concrete types. Second, debug the ordinary function. Before converting the function to a template, make sure it is fully debugged and working correctly with the specific types. This helps isolate any issues related to the algorithm itself rather than template syntax. Third, you can convert to template. Once the function works as intended, replace the specific type names with type parameters to create a template. This allows the function to work with any data type. Now, what are the advantages? So first of all, it is easier to solve concrete cases. It's often simpler to solve a specific problem with a known data type before generalizing it. And you can focus on algorithm. This method allows you to focus on getting the algorithm right first without worrying about template syntax complexities. So first of all, here there are some inappropriate types in templates. So we have to make sure the type is suitable. You can use any type in a template as long as the code makes sense and the type behaves appropriately within the template's logic. So here is an example. For instance, the SOP_values template function cannot be used with types where the assignment operator isn't defined. For instance, arrays cannot be assigned directly, so attempting to swap two arrays using this template would result in an error. So here, that's why it's cross, it's not right, that will give you an error. So you have to remember that templates require the types used to support the operations defined in the template. If a type doesn't support a particular operation like assignment, it cannot be used in the template for that operation. Here we just declared these templates, but so here is the continuation of the generic selection sort example. where we'll see here there is a double array, which double array B is initialized with unsorted double values. The program displays the unsorted doubles. It then sorts the array using the sort function. Finally, the sorted double values are displayed. Similarly, character array C is initialized with unsorted characters, and then so on. So the whole example illustrates the power of templates in C++, as the same sorting function works seamlessly with different data types, showcasing the efficiency and reusability of templated code. Go deep inside this template declaration. I'm just showing you how we are using it, like 3 times one template. So here is another example which demonstrates a simple linear search algorithm implemented in C++. This program allows a user to search for a number in an array and find its position. So you'll see here we have a declared size, a constant defining the size of the array, fill array, which is a function to fill the array with values, search, which is a function that performs a linear search on the array for the given target value. Now inside the main function we have an integer array, array of size declared. Size is declared. Fill array populates the array. The user is prompted to enter a number to search for in the array, which is saved as which is the variable target. Search function is called to find the target in the array. Then if the target is found, its position in the array is displayed. If the target is not found, a message is displayed indicating that the number is not on the list. The user is asked if they want to search again, yes or no, and the process repeats based on their input. So then the program ends when the user decides not to search again. So I'll just go over it for a brief explanation of the code. So the fill array, which fills the array with non-negative integers entered by the user. The parameters like the array to be filled, size, the maximum size of the array, numbers used, a reference variable that tracks how many elements are actually used in the array. Then, as I said, it gets the input from user, and then the loop continues until the user enters a negative number or the array reaches its maximum size. On the search function here, the array to search through, it's a, and then number used, the number of elements used in the array, target, the value to search for in the array. Then the function iterates through the array from the start, comparing each element to the target. If a match is found, the index of the matching element is returned. If the target is not found, the function returns -1. So here is the whole procedure. That's how it just continues until the user says no. So generalization of classes. Just like function templates, you can create class templates to generalize classes. The syntax is template class T, where T is a type parameter. In the class definition, every instance of T is replaced by the actual type specified when an object of the template class is instantiated. So once a class template is defined, you can declare objects of this class by specifying the type. This allows the creation of classes that can work with any data type, making the code more flexible and reusable. So you have to keep that in mind, that class templates enable the creation of generic classes that can handle different data types with the same logic, enhancing the flexibility of your code. So the syntax for defining a class template is similar to that of function templates. It begins with the template class type parameters. Just like in regular classes, you can define member functions and overload operators within a class template. These functions and operators are defined as function templates, meaning they also use the type parameters. So here is an example of class template. The class template is defined using template class T. Here T is the type parameter that will be specified when an object of the class is created. Now class pair, we have a class pair. Here the class pair is designed to store two values of the same type T. It has private data members first and second of type T. Then we have constructor pair T first value, T second value, which initializes the first and second members with the provided values. Then we have some member functions like set first, which updates the first number, set second updates the second member, get first returns the value of first, get second returns the value of second. And then main function, here a pair character object P is created with the values A and B. It prints the initial value of first, changes it using set first Z, and prints the updated value. So this example shows how class templates allow for creating generic classes that work with any data type specified at object instantiation. The class template allows defining a class where the data type of the members is not fixed until the object is created, making the class versatile and reusable. You'll see this is the output here. First is A, then first change to Z. Now you can declare objects of the pair template class for different data types. For example, pair integer score creates a pair object score that holds two integers. Pair character seats creates a pair object seats that holds two characters. Once the objects are created, they can be used like any other object in C++. Like for instance, score dot set first 3, which sets the first value of the score object to 3. Then score sets second 0, sets the second value of the score object to 0. So here each member function definition is itself a template, so it requires a template prefix before each definition. When defining a function member, the class name before the scope resolution operator, this is pair T, not just pair. This indicates that the function is part of a template class with type T. So we also have constructor and destructor. The constructor name remains just pair without T. Similarly, the destructor name without would also just be pair. So let's consider this function which add up, the add up function, which takes a parameter of type pair integer, which is a class template where the type T has been specified as integer. The type integer is supplied to be used for T in defining this class type parameter. The parameter, the pair, is passed by reference as indicated by the AND. The template types can be used anywhere. So template types can be used anywhere standard types can be used. This example demonstrates that you can pass an object of a template class to a function just as you would with any standard type. So here is an example of class templates within function templates. So rather than defining new overload, function now applies to all kind of numbers. So here are some restrictions on type parameter. Here only reasonable types can be substituted for T. Assignment operator must be well behaved. Copy constructor must also work. If T involves pointers, then destructor must be suitable. Similar issues and as function templates. Now here we have type definition. It can define new class name, class type name to represent a specialized class template name. For example, this type definition pair integer, pair of integer, name pair of integer now used to declare objects of type pair. Name can also be used as parameter or anywhere else type name allowed. Now friends and templates. Friends functions can be used with template classes in the same way they are used with ordinary classes. The only requirement is to specify the type parameter appropriately when defining friend functions for template classes. It is very common to define friend function for template classes, particularly for operator overloads, which allows these functions to access private members of the template class. So basically, friend functions are a powerful feature in C++ that allows external functions to access the private and protected members of a class, which is specifically useful when implementing operator overloading in template classes. We declared these templates here, template class T. The main functions start from here, from this slide. If you will go through this whole code, because I already explained the previous codes as an example in details, so this one is for you. You will go through this code and then you will see if you understand or not. It's just the same way we did for the templates. We saw some other examples before, so you'll just go through the code, and here's an output of the code. You'll see how the code's working and how we're getting this output. And if you have any question, you will let me know. So we could have some predefined template class. So if you see vector class, it's a template class. Another one is basic string template class. Look at these two examples, a basic string and then double, and the integer version. Basic string itself is not necessarily limited to only character types. It might be intended to be used for string data. So the last one, if you see the first one, basic string character, basic string double, and then basic string your class. So that will work like that. So this is an explanation of vector. So it's basically recall string is an alternate name for basic string character. All member functions behave similarly for this. It is defined in library string. Definition is in standard namespace. So here for templates and inheritance, there's nothing new here. It is derived template classes. It can derive from template or non-template class. Then derived class, naturally a template class. Syntax same as ordinary class derived from ordinary class. So inheritance is nothing new than templates. It can be derived from template or non-template class. We'll see and to show you the inheritance function. This is how it will inheritance. It can access all public and private functions and members from this class pf array bar, and then it can utilize it as it needed. So you will also go through the whole code, and we have this output here, and then you will let me know if you have any question. So that's all for our lecture 2. I hope you understand properly. Otherwise, you can always email me anytime. We can have a meeting or anything, whatever you prefer. And then you will have an assignment due. You will find the assignment 1, homework 1 on module, and that will be due next week, at the end of next week. So if you have any question regarding the assignment, feel free to ask. Thank you.